Welcome back, everyone. I'm picking up in the limit law section where I left off. And we just spent a long time talking about the properties of limits. We did a few problems dealing with, the limits in generality and using their properties. And we really discovered that ultimately we are just kind of plugging in the limits and going from there, or plugging in the number. So let's see how it works with actual formulas. This says evaluate the following limits using the property of limits. So for this first one, I'm going to go in the detail that I went in above, and that's to just plug in everything based on the properties of the limits. And then I'm going to compare it to what if we had just plugged it in to everywhere we see x -1 in the first place. All right, so let's go ahead and do it. We see a fraction, the limit property that says division means we can do the limit of the top. The limit as x goes to -1 of the top. I'm going to write it in parentheses just so it's more clear that we're distributing it over, and then the limit as x goes to -1 of the bottom. All right, so just distributing the limit to the top and bottom. Now in the top and bottom we have a whole bunch of additions, no subtractions, although it'd be done the same way. We can do the limit of each part. So we do the limit as x goes to -1. X goes to -1 of the first thing, which is x squared, plus the limit as x goes to -1 of the next thing, which is x, plus the limit as x goes to -1 of the last thing, which is just 1, over the limit as x goes to -1 of just x. I probably shouldn't write that too far away so it's not confusing, plus the limit as x goes to -1 of 3. Right. So if you're keeping up, all I did was I distributed the limit over everything, which is what our addition rule says. Now, what do we do everywhere? Well, technically, we can directly plug in everything except this first one, because we know what happens if we have just an x, which is what we have there, or just a number. So let's go ahead and just plug them in. I'm going to leave the first one blank for now. We have plus, and then when we plug in x equals -1 for x, we get -1. We know we can plug it in because it's just x. We know when we do the limit of just a number, which is 1, we always get out the numbers, plus 1. And then on the bottom, the idea is the same. We have just x, so this first thing is -1, plus, and then the second thing here, it's just a number. When we do a limit, we always get the number out, 3. So those were the two base properties. Now we kind of talked about doing this one before when I did that example of sine of x squared. Whenever you have an exponent, you can just plug it in and then raise it to the power, right? So we got -1 is what x is, and it's being raised to the 2 power. And that's really what you want to compare here. Look at, we did 3 steps here, but compared to the beginning, what we started with, to the end. What did we do? Well, look at about it. If we went ahead and just plugged in -1 directly for x everywhere, you would have the same exact thing. And that's the thing I'm trying to stress, is that when you deal with a limit, that's going to be your default thing. You're going to just plug it in. Now, it's not always going to be nice, as we're going to see, and we'll have to do some extra steps, but go ahead and plug it in and then see what you get. So -1 squared is 1. Plus -1, that's -1, and then plus 1 over -1 plus 3. Now 1 minus 1 is 0, plus 1 is 1. -1 plus 3 is 2, and you get 1/2. Right, so if you graph this thing and you looked at the x value going towards -1 from both sides, you would get 1 for each. And that's remarkable compared to where we just talked about introducing limits in the last section. Now we take this complicated looking function and we realize we can just plug it in. We don't have to graph it. We don't have to look at anything. We don't have to plug in close numbers. We just do it. All right, so using that idea, that's how you want to approach number 2. Number 2, I intentionally made look very complicated because, really if you don't see the pattern here of just plugging in, it's very hard. But if we go ahead and plug in pi, right, that's going to be our default. Like I said, let's plug in pi. for x, we get, when we plug in, that's when the limit goes away, by the way. So you should notice that when I'm plugging in here, I keep rewriting the limit until I'm actually plugging it in. So as soon as we plug it in, the limit goes away and we just rewrite everything but with pi for x. We get the natural log of pi plus cosine of pi. Now keep in mind the second parentheses is closing off the natural log. Then we times by e to the pi. Right. Now there's not a lot you can do to simplify here, but you do know cosine of pi, which is -1. We get the natural log of pi plus -1 is -1 times e to the pi. But the rest we can't simplify. Natural log of pi -1 and e to the pi are not nice numbers. Pi goes well with trig functions. It doesn't go well with logs or exponents. But really the emphasis here again is that log functions, exponential functions, trig functions, just plug it in. And one thing you can do to check yourself, go ahead and pull it up. Wolfram Alpha does limits really well. Now I'm not sure if it's going to give it to me in the exact form we got it, but let's just see here. And I can show you how to type it in. So the way I do it is the limit, and then I type in the function. We got the natural log x plus cosine of x times e to the x. And then you write as x to, and then the number, x to pi. And hopefully it reads it correctly. Sometimes it's not going to be perfect, but if you look at what it wrote here on the right, it does say the limit. Let me make this bigger. That didn't work. Zoom in. It does say the limit as log, but notice the log is a natural logarithm, so it is ln. Wolfram Alpha just writes log of x plus cosine of x times e to the x. That's exactly the function we had, so we're doing the right thing, and we get e to the pi times log by ln of -1 plus pi, and that's exactly what we have. We just have it written in a different order, but it's multiplication, so the e to pi could come to the front, and the pi minus 1 is the same thing as -1 plus pi. All right, so really, we're doing well. We can see, ultimately, it looks like limits aren't terrible. It seems like it could have been terrible because based on last section, we were having to graph, we were having to plot numbers when we had a function that we couldn't graph well, or maybe it was just a different technique. Well, unfortunately, not all limits are this easy as you might expect. And there's two big examples as to why limits aren't going to be this easy. The first one is the case when you get 0 over 0. Okay, so next we're going to be talking about the common techniques for limits not evaluated directly, meaning if you plug in, you get some sort of weird number. But we introduced this in the last section, but if you get 0 over 0 when plugging in a limit, this is called indeterminate form. And what this means is the limit can be anything. It could be 0, it could be d and e, it can be infinity, it can be 1, 2, -1, square root of 2, anything at all. There are two common algebraic techniques for these examples, and it's really the only two that we can do at this point. We'll have to wait many sections in the future until we can use other ways. But the two techniques that we can use are factoring, which you're probably very familiar with, hopefully, and rationalizing, which you might have some familiarity with, but is not as commonly practiced at this point. So for the following examples, evaluate the limits. I give you a little hint here to notice that each gives 0 over 0 when plugged in directly, but you should do that. That's a default. You want to plug in your number. So algebraic techniques need to be applied to simplify. And one thing I like to also mention is we talked about this in an example last section, but if your limit is of the form you have a number over 0 where the number is not 0, so 1 over 0, 2 over 0, anything over 0, then that limit is infinite. But if you get 0 over 0, you don't know. So let's go ahead and work this first one. This first one, we want to do the limit as x goes to 3 of x squared minus 8x plus 15 over x minus 3. Now, if it wasn't in the section, you would do your default, plug in. Unless if you know already what's going to happen, because we are in the section, or you can eyeball it, plug it in. We want to plug in x equals 3. We get 3 squared minus 8 times 3 plus 15 over 3 minus 3. Now you can definitely see the denominator 0 pretty quickly, but if the numerator is 0 or not depends how we would proceed. 3 squared is 9, minus 8 times 3 is 24, plus 15, and 9 minus 24 plus 15 is 0. So you get 0 over 0, which is indeterminate form. It is not an answer. And the thing we want to think about is we must factor or rationalize. And this is one where we'll factor. Usually you can tell when you have to rationalize because you have some radicals, which we will at the one below, or fractional exponents. But we must rationalize here, or sorry, factor. When you see that your limit is in indeterminate form, you don't start by just factoring. You have to do it properly. Rewrite the limit itself. Limit as x goes to 3 of x squared minus 8x plus 15 over x minus 3. And until I plug in 3, I'm not going to get rid of this limit. I'm going to keep writing it. What I want to do is factor. The bottom is just x minus 3. There's nothing to factor there. The top, I'll be able to factor. We want the two numbers that multiply to positive 15 and add to negative 8. That would be negative 3 and negative 5. Now, a very, very big hint when you have 0 over 0 is that a factor does need to cancel out. So x minus 3 pretty much needs to be a factor on the top. Right. But notice that I'm just factoring here. I haven't plugged in 3. I'm going to cancel out. The limit, the fact that it's a limit is what allows you to cancel out. And I will explain that when we graph in a second. So I still haven't plugged in. I'm only left with x minus 5 inside. But now that I've factored and canceled, you can tell that if I plug in 3, I'm not going to get 0 over 0 anymore. There's not even a fraction. So I just plug it in now. 3 minus 5 is negative 2. And that is the answer. That is our limit. Right, so why am I making a big deal out about writing the limit every time until you actually plug it in? Well, when you're dealing with a limit, you're not actually plugging in the number. That's what we want to remember. We're just, basically plugging in numbers really, really, really close to 0, but we're never actually plugging in, 3, not 0, but we're never actually plugging in 3. So what I want to do is go ahead and graph our original and graph the x minus 5 and show you the subtle difference. So y equals, we have x squared minus 8x plus 15 divided by x minus 3. Now what we figured out in the first part was that we got 0 over 0 when we plugged in 3. So if you go ahead and look at where x equals 3, looks like it's about right here. You go down to the graph, and the limit does look like negative 2, so we must have done it right. But what happens if you're on 3 exactly is it's undefined. Okay, so this thing is undefined because we're dividing by 0. Now what if we just graph the thing after we canceled? So y equals x minus 5. Well, what you want to notice is it literally went right on top. So if I click back on the green, it's right on top. The purple is our x minus 5. It's right on top. It's the same graph. But what's the difference? If I go to 3, let me see if I can get it exactly. You don't have that undefined anymore. It's negative 2. It seems like a very subtle difference, but if you do not write the limits, what you're actually doing is changing the function barely, but you are changing it. So our original function was undefined at negative 3. After we factored and canceled, our new function, x minus 5, was not undefined at negative 3. And it ends up being our limit value. But if you just write equal signs without the limits. So if I didn't write the limit here, when you cancel out, what you're doing is you're canceling out something that's changing your function. So you need to write the limit every time until you actually plug it in. Once again, doesn't sound like it's going to be important, but it's very, very important. All right. Number two is going to be a common technique that you're probably not as familiar with. It is called rationalizing. But once again, before I even worry about whether we want to simplify it or not, if it's not 0 over 0, you do not have to worry about anything and simplify. So we have to make sure we plug in. And here we are using the variable t, and we want to plug in t as 0. We get the square root of 9 minus 0, then minus 3 on the outside, over 0. Definitely 0 on the bottom. Is it 0 on the top as well? Yeah, because 9 minus 0 is 9, and we got the square root of 9 minus 3. Square root of 9 is 3, so 3 minus 3 is 0 over 0. Well, the thing that's going to indicate that you can't factor here is you should realize that this is not something you can factor. You hopefully were never, I mean, there's very, very, very rare examples where you can factor with a radical, and this is not something we can do. So we're going to do rationalization. Now, some of you may have done it, depending on where you came from. Some of you may not have done this. I'm going to teach it from scratch, but it's really not that bad. I'm going to start by rewriting the limit. And everything that's in it. Now, the way you rationalize is very straightforward. It looks very messy at first, but it's very straightforward. I'm going to put the top also in parentheses. We're going to multiply the top and bottom by something. And that something is going to be this. Take the radical part and rewrite it exactly, but without the minus sign. So what I mean is I'm going to take the 9 minus t and the 3, and I'm going to rewrite them exactly like that. And when you rationalize, what you want to do is actually just change this sign. So if you change that minus to a plus, if it was a plus, we would do minus. You want to multiply the top and bottom by this. Okay. So if you are rationalizing, you just take the sign that's in between and change it to a plus or minus. Depending on whatever the original was, make it the opposite. All right, now how is this going to work? Remember, rewrite the limit every time. On the bottom, I'm not actually going to simplify it at all, and you'll see why as we go through. I'm just going to leave it as t times the square root of 9 minus t plus 3. Now, for a very simplified reason, why I'm not going to simplify this is because it's already factored. Right, but what we want to do on the top is we want to FOIL this. This is a binomial, two things multiplied by two names. We want to FOIL this, and you can do that. Multiply the radicals together first. We get the square root of 9 minus t times the square root of 9 minus t. You should be comfortable with the idea that if you multiply the square root by itself, the square root goes away, and you just get the number to get the stuff inside. So this is just 9 minus t when we do the first part of FOIL. And then when we do the outers, we get the square root of 9 minus t times 3, and it's a plus 3 times the square root of 9 minus t. And then when we multiply the inners, we get the negative 3 times the square root of 9 minus t. So we got minus 3 times the square root of 9 minus t. And then when we do the last, we get negative 3 times 3, which is negative 9. Right. Now what you want to notice is on the top, if you do this correctly, if you multiply by the correct thing, is a lot will cancel out. The square root of 9 minus t, one has a plus 3 and one has a minus 3 attached to it. That's exactly going to cancel out. It's like having 3x and negative 3x. It cancels out. But you can also cancel out even more. Notice that the 9 here, I wrote it in parentheses to just indicate we're at the beginning, but it's not being multiplied by anything. We have this 9, cancels out with this minus 9. Now I'm just canceling. I still haven't plugged in anything. We're doing the limit as t goes to 0, but all that's left on the top is just negative t. Everything else went away except this negative t. And on the bottom, we got t times the square root of 9 minus t plus 3. Now what you can do and what you have to do is something similar to above. Whenever you get 0 over 0 and you do an algebraic manipulation like this, factoring, rationalizing, the 0 over 0 won't go away until you cancel something. And at this point, we can cancel. This t on the bottom gets canceled with the t on the top. Now, because this is pretty much the only thing up here, we just, write a 1 to notice that it's -1 on the top. And I'm going to write in one more step before I plug in. But once we cancel, we are pretty much good to plug in. We have a -1 on the top, and on the bottom, the t went away. We have a square root of 9 minus t plus 3. Now, it might on the face of it not look that great, but you're pretty much guaranteed it's not indeterminate anymore because you can't get 0 over 0. -1's on the top. But now we can plug in. We cancel the t's, we can plug in. We get -1 over the square root of 9 minus 0. Let me go ahead and just write plug in. Plus 3. And then we have -1 on the top still. Square root of 9 is 3. Plus 3 is 6. And the limit is -1/6. Seems like a lot of work, and I'm not saying it isn't a lot of work. It might be very new to you, but rationalizing, you can rationalize the numerator or denominator. This could have been flipped. We would do the same thing. Once again, I think this is a good place to stop, and in the next video, I will finish up this section.